So, welcome back. In the last video we have seen how to solve the heat equation for a semi-infinite domain that is from 0 to infinity with the initial data and boundary data at x equal to 0. So, when you give two different types of boundary data, so whether it is insulated at that end or you maintain the temperature, 0 temperature at that end. So, both the problems are solved by just by extension as extend the functions as even or odd functions depending on the boundary condition, as we have done for the wave equation. So, this technique we have already seen for a wave equation, and then we see that the solution of initial value problem for the heat equation is actually some integral type of solution. So, that integral is actually, so this integral we have just seen that kernel of that integral as a solution is actually nothing but some delta function. That is what we have seen. So, that is related to the delta function, that is what we have seen. So, then we looked at the non-homogeneous heat equation. So, that is what we have here. So, this is the non-homogeneous heat equation, and this we can solve by splitting into two problems. One is the homogeneous problem with this initial data, whatever is given for the non-homogeneous problem, and the other problem is U2, that is satisfies non-homogeneous equation with 0 initial data. So, that is the domain is full domain, x belongs to full R. So, what you have is the full R. So, if we know the solution for the initial value problem for the homogeneous equation, so that is actually the heat equation that we know, that is the solution. And only what we do not know is this second part. So, U2 we do not know. So, if we solve this U2, we can combine this U1 and U2 to give the solution of the initial value problem for the non-homogeneous heat equation. So, we will see how to solve this here. So, look at this. So, what we need is this one. So, to solve this or for that matter, so this is a non-homogeneous equation. So, if you want to solve this, we know that if you take let us take this non-homogeneous problem. Simply you take the non-homogeneous problem ut minus alpha square utt equal to 0 equal to non-homogeneous problem, that is h of xt, x belongs to R, t positive. Okay. So, and u at x0 is, let us say, some fx. So, this is the non-homogeneous problem, and uniqueness, this has a unique solution, has at most one solution. Okay. At most one solution, because we have not find the solution for this non-homogeneous equation. So, we cannot say whether it has a solution, but you can say that it has at most one solution with this. So, not more than two solutions you have for this problem. Okay. That we can easily show just by taking u1 is one solution. Let u1 of xt and u2 of xt be two solutions, and then as usual you consider w of xt as u1 of xt minus u2 of xt. So, if you do this, satisfies the heat equation. So, Wt minus alpha square Wxx. So, u1t minus alpha square u1xx is actually h of xt, and similarly u2t minus alpha square u2xx is also h of xt. So, now this becomes homogeneous. W satisfies the homogeneous equation, and the W at x0 is also, so that is 0, initial condition is also 0. So, we have seen by the energy argument that this problem has a 0 solution, has a unique solution. Okay. Homogeneous equation with the initial data has a unique solution, Okay. So, we know that this has this solution, this homogeneous equation with the initial data has a unique solution, and clearly 0 satisfies this. So, Wx of t is completely 0 for every xt, satisfies this problem. Okay. So, the above problem, above initial value problem. So, that means this should be the unique solution. So, that implies u1 has to be u1 of x t equal to u2 of x t. So, this means non-homogeneous equation, this one, the non-homogeneous equation with the initial data has at most one solution. So, if you can construct one solution, so that should be, if you can construct a solution, that should be the unique solution for this problem. So, if I construct in a notorious way, okay, so some special way I try to construct a solution for this non-homogeneous equation with actually not this one. So, we try to find non-homogeneous, we try to find the non-homogeneous solution, we try to find a solution for this non-homogeneous equation with 0 initial data. So, u2 we will try to get it. So, once you get this u2, now if you take f equal to 0 here, now we know that if you choose in particular f is 0, then this problem has at most one solution. Now, if I construct one solution, so that means you have the solution, okay. So, you have a unique solution. How do we do this? So, we try to find in the solution for this u2 in a special way. So, let me construct something similar. Similar is you consider du by dt. So, let us say u is let us call this not u, some other function. So, let us say y of x, let y of x is y is a dependent variable, x is independent variable. Now, consider this linear equation dy by dx equal to dy by dx minus a times y, a is a constant, okay, equal to, and y is a function of x. So, you have a non-homogeneous term, that is h of x. So, let us see this is some x positive, let us say, okay. So, if you want positive, so you can say if you want t is a time. So, as a time you can have this t positive, so that you have a t positive, okay. So, this if you have, and initially you have a t equal to 0, initially you have some constant. So, let us say c, a constant, okay, a constant. So, what is the solution here? So, how do we find this solution for this ordinary differential equation? So, consider this ODE with the initial data, with initial condition, initial data. So, if you see this, we know that e power minus a t is integrating factor, so that you can multiply this y of t. So, this is the derivative of this. You just multiply e power minus a t both sides, what you get is e power minus a t h of t, okay. So, now you integrate both sides, this is t, okay. So, you can integrate now both sides from 0 to t. So, t is positive. So, 0 to t. Now, here inside t is a dummy variable. So, I can write as a s h of s ds, okay. So, this will give me my solution as e power minus a t y of t minus e power a into 0, that is 1. So, you have y at 0, that is c, okay. So, that is c. So, if you bring it to the other side, that is equal to c times c plus integral 0 to t e power minus a s h of s ds, okay. So, what is the solution now? Y of t is c into e power a t plus e power a t is a function that is outside. You can take it inside integrand, that is only variable functions that whose variable is s, integration variable is s. If you combine this e power minus a t e power a s, so what you get is e power minus a s minus t or e power a t minus s h of s ds. So, you can see that for this problem, this is called a propagator. E power a t, this function is a propagator. So, it takes this initial data plus, and it also takes acts on this propagator operator is acting on the non-homogeneous data. So, something. So, along with this we can draw parallel to this this kind of whatever is happening here for this ordinary differential equation with the initial data. Okay. So, if you can do the can draw the parallel for the heat equation along these lines. So, what is the equation corresponding? So, we just write, I will just write it parallel to this. What you have is u to t minus alpha square u to xx equal to h of xt. So, this is what you have. So, x belongs to R, t positive. So, this is my problem for u2, and what is the initial data? u2 at x0 equal to 0. That is exactly my u2 of x0 is 0. So, this is what is the initial data. Okay. Or let us choose some data. So, some function of x, let us not give simply initial. So, that is for u. So, u2. So, let us consider only u. We will solve we will consider this u2 as a special case. Okay. So, you let us say u solves this non-homogeneous problem with this initial data. Now, if you draw parallel here with this, okay. So, if you see here correspondence here, what you have. So, how does it look? So, what is the solution? So, this is actually e power at is a solution of if h is 0, if h is 0, then this is the solution. This is the solution of homogeneous equation with the initial data. So, I know if h is 0, I know its solution. Okay. So, that solution is that my propagator. Okay. So, in this case what is the question is what is the propagator? So, propagator so the propagator here is actually, if you see this is, if this is a propagator, this actually solves the homogeneous equation with the initial data. Okay. This actually solves the homogeneous equation with the initial data. So, what is the homogeneous equation here? So, if I consider here should be satisfying ut minus alpha square, here should satisfies ut minus alpha square uxx equal to 0. I consider homogeneous and the initial data is fx. Okay. So, this should be the propagator here satisfies like this. So, if I draw the parallel here, e power at satisfies homogeneous equation. Okay. Initial data is different. So, c into c, that is okay. So, you can write this is a constant, I can write it here. So, this is an operator, propagator operator. If you view like this, e power at acts on the constant, the initial data c. Okay. So, homogeneous equation with the initial data. So, the propagator is this one, homogeneous solution acting on the initial data. So, what happens here? I know the solution here u of xt is actually what is the solution for this initial value problem, which we know, that is from minus infinity to infinity s of x minus y comma t and fs ds fy dy. So, this is what is my homogeneous solution with this initial data. So, this should be my propagator. So, propagator here is this one. Okay. So, this is the propagator here. So, this is the operator. So, operator acting on the initial data. So, I can write this propagator operator as here some capital F propagator operator on this f of xt, f of x, right, propagator operator. So, let us say which is a function of t, like here e power at is function of t. Okay. So, let me put it as a script. So, script is script of function of t and then acting on f of acting on fx, okay, acting on fx. If you acting on fx, that should be finally a function of x. Okay. So, acting, it takes fx, x is from minus infinity to infinity to finally another function of x, of course t is also there. So, this is the propagating operator. I am just guessing, okay. So, just based on this something here for the ODE, we see that this is the propagating operator. So, in this case this is which is actually homogeneous solution acting on this. So, e power at c is the propagating operator acting on the initial data c. So, we draw the parallel here. So, this is the propagating operator. So, if this is the case, now you look at this one and you can say what is the solution of the non-homogeneous equation. So, if I take initial data 0, so this will not be there, what is left here is this one. So, this should be non-homogeneous solution if you choose this initial data as 0, okay. If you take initial data 0, so if you take initial data 0, c equal to 0, okay, c equal to 0, if you take this part will not contribute, only non-homogeneous term. So, if you can write this, now the solution of the initial data. So, you can write u2 solution, that is alpha square u2 xx equal to xt. This is the non-homogeneous equation, and then with the initial data is 0. So, this one you can get now, you can write as this part. So, that implies u2 of xt is, now what is this one? This is actually integral 0 to t here. Now, what is my propagating operator? So, I have a propagating function f of, so this f of t minus s acting on h of s. What is h of s here? So, that is non-homogeneous term. Here my propagating operator is acting on the function f x, okay, which is x variable in this integral. So, okay, so this is t minus s acting on h of x t, okay, d. So, what is the finally ds? So, t is the dummy variable. So, t is actually should be s, right. So, t should be t you are integrating. So, the t variable you are integrating, okay. So, instead of this let me write the completely here. So, what is this f of? So, if you see e power a into t minus s, that is actually minus infinity to infinity s of x minus y, in the place of t I have t minus s. Now, this propagating operator is acting on the initial data f of y. So, here it should be acting on the non-homogeneous data, non-homogeneous data, that is h of x t. So, if you act on f x, that is f of y here inside the integral. If it acts on the h of x t, it should be function of h of y, and this should be t, okay. This is actually t acting on t, and that is dy. This should be function of t that you are integrating from 0 to t, okay. So, wherever t is there, I am just putting s. So, this is s, this should be s ds. You consider this one as, so if you consider this, so if you act this, you use this propagating operator acting on this non-homogeneous data h of x t, then this operator acting on h of x t. So, wherever t is there, okay, so t is the derivative here. So, that is actually so independent variable here. So, h of s. So, wherever t is there, you have s. So, that is why, so operator wherever when propagating operator acting on this h of x variable will become y, and t variable is actually become s, as if you see here, okay. So, this is how, this is how I guess, okay. This is what my guess is. This is what is my guess as a solution of the problem that I am looking for, okay, just by looking at this ordinary differential equation with this initial data. So, I cannot say this is the solution, this is how I found the solution, this is the notorious way of getting it, okay. Just I am just guessing that this is the solution. So, if you want to say that this is the solution, you just have to verify it, okay. So, so what you have to say that it has to satisfy this problem, this initial this non-homogeneous equation with this 0 initial data. So, you can easily see that at t equal to 0, 0 to 0 this integral it has to be 0. So, clearly it satisfies u2, this satisfies this initial data, and you just have to see that it satisfies the non-homogeneous equation. So, for that you calculate u2t of xt, u2t you calculate. So, what is this one? u2t, if you do, I am differentiating this t. So, if you do this, if you differentiate this, you differentiate this Leibniz rule, you differentiate this ddt of this ddt of t, that is 1, and wherever s is there, s is the variable, this is the integrating variable for this integral 0 to t, wherever s is there you put t. So, if you do that, what remains is the first one is s of x minus y, t minus t, that is 0, and h of y, s is t, y of t dy, that is what you have, plus now you can integrate whatever is the integrand. So, integrand is a function of t, so that you can integrate. So, now you can write the integral 0 to t dou t of this integration. So, this integral, whole integral, you are just integrating with respect to s, with respect to t, h of ys dy ds, a simple integration, and then you are okay. So, you just took this t derivative inside, that is what you have, and you can see that that we know yesterday we have seen that, we see that s of x minus y 0 is nothing but your delta function. So, you have minus infinity infinity delta function of x minus y acting on h of yt dy plus, and this now if you see this one, so dou t of this function s of, you see that s of x minus y and t minus s satisfies the heat equation. How do we see this? S t minus alpha square s x x is actually equal to s t is now t minus s, okay. We know that s of x t is satisfying heat equation. Now, you want to show that this is also satisfying the heat equation. So, for that you need s t. So, s is this one, okay. So, s is a function of x minus, so this you call this s1 of x t as this one. So, if you do that s1 t and you want to calculate s1 x x. So, what you get is s1 with respect to t minus s dt minus s by dt, that is what is s1 t. So, that is simply 1 minus alpha square s1 x x. So, that is s1 x x is x minus y is one variable, x minus y is another variable. So, there is like d square s1 by d x minus y whole square, okay, something like that. So, but we know that, so this is exactly equal to s1 of this is simply exactly if you replace t1s by some t variable and this x1 by some x variable, this is nothing but st minus alpha square s x x. So, this we know that is 0 because s of x t is satisfying the heat equation. So, in that sense s of x minus y t minus s is also satisfying the heat equation, okay. So, you can actually take this derivative inside and you can write dou t here. So, if you do that, okay. So, if you do this one, because it satisfies the heat equation, so you can see that 0 to t minus infinity infinity. Now, S t is nothing but alpha square, that you can write it as alpha square dou square by dou x square of s of x minus y t minus s h of y s dy ds. So, this is now if you operate this delta, this is nothing but h of x t plus alpha square. Now, this one what is this one? This is actually equal to alpha square into, now I can take this dou, see this integral is from minus infinity to infinity, this is 0 to t. So, I can take this dou square by dou x square outside. So, I can write this outside here. So, dou square by dou x square I can write it outside. So, now whatever is here, this dy integral is nothing but your what is this one? Dou y integral is what is this dou y integral? Actually you can take it outside. So, not just here, you can write actually so this that see this st is sxx. So, the dou square by dou x square I can even write dou square by dou x square outside. So, this whole thing is nothing but your u2. So, that means u2 xx what you have. So, this implies u2t minus alpha square u2 xx is nothing but h of xt. So, that means u2, that is this satisfies the non-homogeneous heat equation, that is this, and it also satisfies when t equal to 0 it is simply 0. So, it satisfies this one, this problem. So, you have this problem is solved. So, u2 satisfies that initial value problem. So, once you know this u2, you can write your solution of the non-homogeneous equation with the initial data as fx. So, that you can write as u1 plus u2. So, this implies u of xt is u of xt. So, that satisfies ut minus alpha square uxx equal to 0, x belongs to R, t positive, sorry this is this should be h of xt, non-homogeneous equation, and u at x0 equal to fx. So, if you have this problem, if you satisfying this, what you get is the u of xt is u1. u1 is the homogeneous equation with the initial data fx. So, that is simply minus infinity to infinity s of x minus y t acting on fy dy. So, that should be your solution plus this whatever you found as u2. So, u2 is this one integral 0 to t, now integral minus infinity to infinity s of x minus y t minus s. Now, this is on the non-homogeneous term h of y s ds dy first and then ds. ds s is the integrating variable from 0 to t. So, this is my solution for the non-homogeneous problem. Okay. This is the required problem. So, this is the required problem, required solution for this non-homogeneous heat equation with the initial data fx. Okay. So, this is how you can find. So, this is what you the technique that you used. You draw parallel to this initial value problem for the ordinary differential equation and just guessed one solution, and you just verified that it is a solution, because it is a solution is unique and you cannot have more than one solution. Okay. And I have a solution, I see that it is a solution, you cannot have more than one solution. Okay. We have shown that it has only at most one solution, whatever it is. So, I give you that solution by guessing it, and by verifying it, it is actually a solution. So, that means it is the unique solution. So, you have the unique solution for u2 and you know that this is the unique solution for the u1 problem. So, finally, the u is for this problem, this has the unique solution. Okay. So far we have considered infinite rod minus infinity to infinity for this non-homogeneous equation. So, you can also do same thing on the semi-infinite line 0 to infinity. Semi-infinite rod you can have non-homogeneous equation. So, let us consider ut minus alpha square u xx equal to 0, x is positive. So, x is this is the semi-infinite rod and t is positive. So, now you have the initial data as fx, and let us say here, so far we have considered only 0, u is 0 or ux equal to 0, either you insulate or you keep the temperature 0. Why should I do that? So, you can have a general condition u at 0 t as some p of t. So, if you have that boundary condition, general boundary condition, still you can show that you can solve this problem. Okay. So, this is the initial boundary value problem for the heat equation, non-homogeneous heat equation. You can also have the non-homogeneous equation, some source is also there, some h of x t. Okay. How do I do this one? So, what you do is, let us consider I want to make this boundary as a 0. If I have the boundary 0, then I know that its solution. So, let us solve that one first. Okay. So, if you do this, so let v of x t be the u of x t minus this p of t, if you take this one. So, that v of x 0 equal to 0 is p t minus p t, that is 0. Okay. So, u at x 0 minus p of t. So, but u at 0 t is p of t minus p of t. So, that is 0. Okay. So, you can see that initial data is this, and this satisfies if you, because u satisfying the non-homogeneous equation, what happens to, so this gives me u of x t is v of x t plus p of t. So, since this satisfies the non-homogeneous equation, and what you see is this implies v t, okay, v t plus p t, that is the first step. Okay. v t plus p t, p is a function of t. So, there is simply p dash of t. Okay. p t means p dash of t, the time derivative of p of t. This is this, because if you put at u t minus alpha square u x x. U x x is because once you differentiate this p t with respect to x, it will become 0. That is simply v x x equal to h of x t. So, this implies v t minus alpha square v x x equal to h of x t minus p of p t. Okay. So, v satisfies non-homogeneous term becomes this, x is again, x is positive, t is positive. So, domain is not changing. So, what you have is this one. So, v satisfies this equation, and I see that this initial data is v at x 0 equal to 0. Okay. Initial not initial data, this should be boundary data, right, v at 0 t, this is 0 t, u at 0 t is p t. So, the boundary data becomes this one, boundary condition is this. What happens to the initial condition? Initial condition is initial condition u at x 0 is f x. So, v at, this should be the boundary. So, you have 0 t is this, and v at x 0 is nothing but u at x 0, that is f x minus p at 0, that is simply a constant. Okay. So, you call this some g x, okay. This you call it some h 1 non-homogeneous term as some h 1 of x t. So, this is what is now the problem. So, if you use this transformation, what you get is the transformed initial boundary value problem. Okay. So, the transformed initial boundary value problem is, it satisfies this non-homogeneous equation, boundary data is 0 now, and initial condition is, initially you have the velocity some g x satisfying. Okay. So, because this boundary condition is 0, you can extend these functions involved h 1 and v and g, you extend as an odd functions, okay, and then make use of the solution of the non-homogeneous solution with the initial data. Okay. That is what we derived here. So, use this one, this is now, this is true for every x belongs to R and t positive. What we need is for only t x positive. Okay. So, if for x positive, if you want to have this solution, this boundary condition is automatically satisfied if you actually extend these functions v and h 1 and g, you extend as an odd functions. This is the technique I have done even for wave equation and earlier heat equation with for the homogeneous heat equation. Okay. So, if you just do this extension, odd extension of these functions, unknown function v of x t and the non-homogeneous function h1 of x t, you extend as a odd function on the from 0 to infinity to minus infinity to infinity. Okay. So, you can do that. So, if you do this one, so odd extension is I simply give you the outline. Odd extension is, let us call this v1 of x t is simply v of x t if x is positive. So, that is what we have, that is the function what we want, and you have v of minus x t if x is negative. So, you extend it like this. Similarly, you do it for h1 of x t. h1 of x t, the odd extension, let me call this odd, v odd. Okay. So, similarly h1 odd extension is something like h1 of x t if x is positive and minus h1 of minus x t if x is negative. So, do it like this, so that x equal to 0 is actually value is 0, okay, for all time t. So, that you need not worry, just one point. So, you have a g also you extend. So, g odd you extend as a function of x as g of x if x is positive, that is what we have for x positive, okay, and now minus g of minus x as x negative. Now, what happens, v odd also satisfies this non-homogeneous equation now, because for x positive this satisfies non-homogeneous equation, and you can easily see that x negative, this is minus v of minus x t, that also satisfies this equation. Okay. But of course, your what happens, your this satisfies the difference. So, you will see how what v odd satisfies. V odd actually satisfies v odd t minus alpha square v odd function. V odd is a function of x t. So, that is x x is actually equal to h1 of x t for x positive. Okay. That is what is clearly you can see, because it satisfies for x positive, v satisfies this non-homogeneous equation. Otherwise what is that it satisfies? Minus h of minus h1 of minus x t. Okay. So, if you see that one, if you actually substitute and see this one minus v t, that is minus is there. So, I have a minus common. So, if you simply substitute this part into this equation, okay, if you simply substitute into the v t minus alpha square v x x, for this function you calculate time derivative and two x derivatives, and you take this v t whatever for this function time derivative minus alpha square 2x derivatives of this function, what you see is a minus is common, and what you get is this is a simply satisfying minus of h of, in the place of x you have minus x. So, you have h1, that is nothing but h1 of minus x t, and x is negative. This is we already extended as an odd function, this is nothing but h1 odd of x of t. So, this satisfies this non-homogeneous equation, and you have this boundary condition is automatically satisfied now. Okay. This is 0 because it is an odd function, extension is odd. So, at x equal to 0 for all times it is 0. So, boundary condition is automatically satisfied. Now, you have to see what is this v x 0. So, v odd at x at time t equal to 0 is nothing but, if you see this one. So, this is nothing but v odd is, if you see t equal to 0, this becomes g x and minus g of minus x, that is nothing but g odd. So, you extend it as an odd functions, and what you got is this. Now, this is for every x belongs to full real line and t positive. This problem we solved just now. Okay. So, this is the solution for such problem. So, this is exactly this one, you have the non-homogeneous equation with non-homogeneous data. So, this is your solution. Once you write in this as a solution there, and then restrict x to only positive side. So, x positive whatever is that is your solution. So, we can write that. So, v of x t, what we are looking for is only for x positive is v odd of x t restricted to x positive. What is this one? V of what is V odd x of t? This is you can have minus infinity infinity s of x minus y t acting on this g odd of y dy. This is my earlier problem. So, it is a u1 homogeneous solution with this initial data plus non-homogeneous solution with the 0 initial data, that is 0 to t minus infinity infinity s of x minus y t minus s. Now, you have h1 odd of y s dy and ds. You simply substitute now what is your h1 g odd and h1 odd, and you can simply see that. So, this is what is your solution. So, and wherever x is there, x is always positive. So, x is always positive. Okay. This is what is the solution. This is what you want for x positive only, you want this problem. Okay. So, you restrict this. This is actually, this expression is valid for even x negative, but your solution is only for x positive. Okay. So, this x positive, wherever x is, that is x only positive, and g odd, this integral you can split from 0 to infinity. G odd is g of y, minus infinity to 0, g odd is minus g of minus y, and you can do the simplification and write this is your, then this should be your the required solution. Okay. This is the required solution. After simplification you can do by just substituting g odd and splitting this integral z to 0 to infinity and minus infinity to 0, make use of this g odd function. So, g odd is gx if it is positive, g of minus g of minus x as negative. So, if you substitute it will take a different form that you can do yourself. So, okay, is the required solution. So, this is actually what is the solution? This is the solution for this general non-homogeneous equation with the boundary condition is the general data. So, this is at that point you need not be simply, you need not maintain the 0 temperature. So, the semi infinite rod at one end you need not maintain the 0 temperature or you insulate it. You can maintain a constant temperature or you can actually change the temperature over a time. So, as a function p of t in general. If you do that, this problem has a solution, and that is we have seen that is also unique. Okay. So, one can show that is also unique because you reduce this problem into this type. Okay. So, this one, and this problem has a unique solution. Okay. So, this implies this also has a unique solution. So, because this problem, this is what we have seen, this problem is having a unique solution if the boundary data is 0, that is what we have seen already. So, that energy argument with one end when you kept it 0 temperature or insulated, you know that solution is unique. So, you reduce this general problem into this type, and this has a unique solution. That implies finally if V is unique, U is also unique. Okay. So, this is how this problem, general problem is also you have a unique solution. The solution is constructed here in this fashion. Okay. So, this is how we can solve sum of the boundary and initial value problem for the heat equation. Heat equation is one dimensional. Okay. So, when the domain is unbounded, that is minus infinity infinity or semi infinite. So, in the next video we can have we can solve the heat equation in a finite interval. So, that is you can consider that is like a situation like you have a finite rod, and initially you give the temperature on it, and then you have two boundaries, both the ends you can maintain 0 temperature or same temperature, or you can insulate one end, you can keep other end you can keep maintain some temperature, or you can actually in general you can maintain P of t, one side P of t, one end you always maintain as a temperature as P of t, other end Q of t for all times, it is varying over a time. Okay. And then what is the diffusion, what is the how the temperature varies over a time. So, that is exactly solving the boundary value problem, initial boundary value problem for the heat equation in a finite domain 0 to L, that is a rod. Okay. 0 to L with the boundary data, that is u at 0 t is P of t, u at L t is Q of t. So, this and the initially you give what is the temperature at T equal to 0, what is the temperature of the rod, that is some function of x. So this general problem you can solve it by extracting a Sturm-Liouville problem out of it, because it is a finite domain. That is what we have seen for the wave equation also. Okay. So this heat equation, heat boundary value problem, boundary initial value problems, initial boundary value problem for the heat equation in a finite domain, we can always extract a Sturm-Liouville problem and then finding eigenvalues and eigenfunctions, and then make a superposition principle, we can find the solution, separation of variable solution. Okay. Separation of variable solutions for this partial differential equation, that is a heat equation here with that satisfies the initial and boundary conditions. That is what we will see in the next video. Okay. Thank you very much.